The Monty Hall Problem by Timothy Felton, Drew Hay, and Andrew Zmijewski. Suppose you have 3 doors to choose from, 1 with a car and 2 with a goat. You choose one door, then one with a goat behind it is revealed. Assuming you want the car and given the option to switch, do you? The Monty Hall Problem was first popularized by Marilyn Vos Savant in her newspaper column, Ask Marilyn. Marilyn Vos Savant was considered the world's smartest woman, so her column in Parade magazine garnered a lot of attention. She responded with the correct answer and proceeded to receive thousands of letters from people, many with PhDs, telling her she was wrong. In the end, though, she was right and defended herself well, and many of her haters subsequently changed their minds and/or apologized.
Before we explain the probabilities behind this problem, what do you think is a better strategy, staying or switching? Does it matter? Additionally, we hosted our own version of the Monty Hall Problem and asked some fellow Governor School students what they thought.
Welcome to the game show. Underneath one of these 3 boxes there is a prize and the other 2 contain nothing. So I need you to point to the box that you think has the prize. Alright, so I know where the prize is located and I'm going to reveal one of the boxes that does not contain the prize. Now, do you want to stay with your original choice, or do you want to switch to the other box?
Switch.
Alright. Oh no, you lost.
I'll stick with it.
You win. Congratulations.
Switch.
You win. Good job.
I'm gonna stick with it.
You win. Good job.
Switch.
You win. Good job.
Or do you want to switch?
Stick with it.
Alright, let's see. Did you win?
Aww. Stick with the box I chose.
Alright. You win!
I'm gonna stick with my original choice.
Oh no! So, at the start of the game, there's 3 boxes, so naturally the chances of winning are 1 in 3, right? So now, when I reveal one of them that doesn't have the prize, what do you think your odds are? Do they change at all?
Yes.
Alright, and then what do you think it is, 50-50 or
50-50.
What if I told you it's actually 1 in 3 and 2 in 3?
What?
I would like to say thank you for participating in my game show, and congrats on winning.
Thank you.
As you may have heard in the video, one of the strategies wins 1 out of 3 times, while the other strategy wins 2 out of 3 times. The Monty Hall Problem is notorious for having a confusing explanation, so we will explain the probabilities through various methods, including a simple explanation, a diagram, a mathematical theorem, and finally, a simulation of the game. Marilyn claimed that switching had a 2 in 3 chance of winning. Many doubted this due to the intuitive assumption that the chances would be 1 in 2. However, Marilyn was correct. If you always switch, the only way to lose is to initially choose the door with the car. Since the chances of this happening are 1 in 3, since there's only 1 car out of 3 doors, 1 minus 1 in 3 is 2 in 3.
This diagram illustrates why it is better to switch. Assume you chose door 1 every time. This does not change the probability. There's a 1 in 3 chance of choosing each of the 3 prizes. If you chose a goat, there's a 100% chance that the other goat will then be revealed. There is a 1/3 probability of each of those sequences happening. In these cases, you should switch because you chose a goat. In the 1/3 of the time where you did choose a car, each goat will be revealed in 1/2 of the outcomes, or 1/6 of the total outcomes. In these cases, you should stay, but since they only account for 1/3 of the outcomes, switching remains the better strategy as it wins 2/3 of the time.
This probability can also be explained using Bayes' theorem, which is an explanation of conditional probability. Bayes' theorem states that the probability of event A given event B, denoted by the bar on the left, is equal to the probability of event B given event A occurs, multiplied by the unconditional probability of A, all divided by the unconditional probability that event B occurs. We can apply this to the Monty Hall problem for any given initial door and any door opened by Monty. However, these will all be equivalent probabilities. For this example, then, we can suppose that we chose door 1 and Monty revealed door 2, again denoted by the notation on the left. What is the probability that the car is behind door 1? Using Bayes' theorem, we know that this probability is equal to the probability that Monty opens door 2, given that there's a car behind door 1, times the unconditional probability that there is a car behind door 1, divided by the unconditional probability Monty opens door 2. The probability that Monty opens door 2, shown on the bottom of the fraction, can be expanded to the probability that Monty opens door 2 if the car is behind door 1, plus the probability Monty opens door 2 if the car is behind door 2, plus the probability he opens door 2 if the car is behind door 3. All of these would be multiplied by the unconditional probability that the car is behind that door. Since this unconditional probability will be 1/3 for all doors, we can take the unconditional probability that the car will be behind a certain door out of the equation, including the top of the fraction. The probabilities can then be plugged into the equation, resulting in a 1/3 probability that the car is behind door 1 if Monty picks door 2. This would also extend no matter what door the car is behind or what door Monty picks. And since the total probability will always equal 1, and switching is the only other option, switching will result in a 2/3 chance of picking the car.
If you're still confused by the probabilities, here are some simulations of the problem. We ran 300 trials using each strategy. On the left, we selected the same door every time. On the right, we switched doors every time. In the end, staying won about 35% of the 300 games, while switching won 67% of the 300 games. The simulation's odds are slightly inaccurate due to the low sample size. However, it is clear that switching is the better strategy. Now that we've thoroughly explained the original Monty Hall problem, let's take a look at some variations.
The first variation which we will look at is called the progressive Monty Hall problem. Instead of having 3 doors, suppose we have n many doors, where n can be any number from 3 to infinity. What if you could switch doors more than once? Would you want to? The first variation we will examine is staying until the last chance you have until switching. If you think about it, this is really the same as the original game with 3 doors, where you do technically wait to switch until your last chance. So, in this game, if you stay on your door, the probability that it contains a car stays the same as it was in the very beginning, regardless of how many doors there were, while the probability of the other doors increase as more goats are revealed. For example, if there are 100 doors, there would be a 1 in 100 chance that you originally chose a car. Monty Hall would then reveal 98 goats. There is still a 1 in 100 chance that you chose correctly from the beginning, so there is a 99 in 100 chance that the remaining door has the car behind it. Therefore, staying on the same door then switching at the last chance will mean that you have a 1 over n chance of losing, or a chance of n minus 1 over n to win, and this is the optimal strategy. Here is an example of this problem with 5 doors. When you choose your door, there is a 1 in 5 chance that it has the car behind it, which is the same as the other 4 doors. But when one door is removed, there is still a 4 in 5 chance that you did not pick the correct door to begin with. So that is split among the other 3 doors, leaving them each with a 4 in 15 chance of having the car behind it. Then another door is removed, so the 4 in 5 chance is split between just 2 doors, so that they both have a 2 in 5 chance of having the car behind them. And then one more is removed, and so the 4 in 5 chance rests entirely on one door, and now, in your last chance, you should switch, which will leave you with a 4 in 5 chance of winning, which is also equal to n minus 1 over n.
While waiting till the last moment to switch may be the most efficient strategy, there are other strategies as well, which we can also compute the probability for. One of these, which we will discuss now, is switching every time that you can. By finding that the probability of winning if you initially pick a car is the same as your probability of winning if your first switch is onto a goat, since you are guaranteed to switch onto a goat, we can derive the probability of winning if you switch every time as represented by the negative sum of negative 1 to the I divided by I factorial, as I goes from 1 to infinity, shown here. By using Taylor series, we can calculate that as the number of doors increases towards infinity, the probability that you will win nears 1 minus 1 over e. 1 minus 1 over e is roughly 0.6321, and as we can see here, that as the number of doors increases, the probability rapidly nears this number.
Now let's talk about another interesting variation of the problem called lazy Monty Hall. Assume you chose door 1 every time. In this variation, Monty Hall favors door 2 and opens it 75% of the time when given the chance. When you choose a goat to begin with, Monty will be forced to open the door with the goat behind it, so it is 50-50 between doors 2 and 3. When you have chosen the car, that is when there's a 75% chance of door 2 being chosen. This means that there is a 7 in 12 chance that door 2 will be revealed overall, and a 5 in 12 chance that door 3 will be revealed. When door 2 is revealed, there is a 4 in 7 chance that you should switch. When door 3 is revealed, there is a 4 in 5 chance that you should switch. And so overall, there is a 2 in 3 chance that you should switch. The overall percentage stays the same, but it does change for individual doors, which is very interesting.
The last variation we will explore is where Monty Hall has a tell, such as arching his left eyebrow 3 times. If the player selects the door with the car, Monty will give his tell 95% of the time. However, Monty will fake the player out by giving a false tell 10% of the time if the player selects a goat door instead. The tell will happen 19 out of 20 times that you choose the car, and 2 out of 20 times that you choose a goat. It will happen 23 out of 60 times overall. You would want to stay for the 19 out of 23 times that the tell was an honest one, which gives you an 82% chance of winning. There are 37 out of 60 times where Monty does not give a tell, and only one of those times was it the case that he didn't give a tell when he was supposed to. This means you should switch 36 out of 37, or 97% of the time, that he does not give a tell. Here are the sources we used in the research and creation of this video.